Okay, doke. About that time? Well, good afternoon, everybody. Hope everybody's doing well this afternoon. This is Psych 301 Research, Design, and Methodology. I hope everybody's doing well today. It's March 30th, 2020. What we're going to do today, let me talk about a couple things before we start. Number one, y'all have been sending in your stats quizzes, and that's great. I think almost all of them have been legible so far, and I wrote to the people who are illegible for the ones who've sent them in. If you are planning to mail it to me through the mail, I would appreciate it you sending me an email, and my email address is ecooper@iastate.edu, sending me an email telling me that your Stats Quiz 2 is coming through the mail, so I'll be sure to look for it in my mailbox. So I appreciate if you do that. So I'm going to wait for all the stats quizzes to come in before I grade them. And so I'll probably grade them on Wednesday morning. So look for your stats quiz grade on Wednesday morning is what I would say. Okay? Okay, well, now we're going to talk about what we're going to talk about today. And we're kind of doing this in, it's kind of a two-part lecture. There are two videos associated with this lecture. Now, I don't have a webcam at home, and so it was hard to do the stats tests, and I didn't know how we were going to do them. We are going to learn a new stats test today, so and I put up the directions for that stats test. Those are available on the front page of the Canvas site. But what we're going to be talking about this week is we're going to be talking about correlation. That's our big correlation. That's our big topic this week. And what you're going to have to do is you're going to have to learn after this part, my part of the lecture, since the TA has a webcam and he's actually seen me do the stats tests and stuff, I had the TA make a video of how to use the correlational approach. And so after you're done with this, then you need to watch the video, and I put the link in the announcement that I sent out for this video for that one. You need to watch that video and ideally work the problem along with the TA. He's doing one of the problems in the back, and so you should get out your calculator and work it along with him. But he made a really, really good video for how to do that particular test. So we're going to have Stats Quiz 3 in a little while, a few weeks, and then that correlational test will be fair game for Stats Quiz 3. But what I'm going to do right now, before you go watch the video about how to do correlation, we're going to talk about what correlation is first. So we talked about one of the research techniques that we've talked about is the correlational approach. The correlational approach. Oh yeah, and I thought things were a little bit boring, and so I'm going to put up a picture of Rosie. This is my dog Rosie. This is when she was a little puppy. Here, I'll put up a picture of Rosie every day to try and make the videos a little bit more fun, maybe. More visually interesting, anyway. All right, well, back to this. Correlational approach. That's a research technique in which the researcher determines if variables are related without manipulating the variables. I got the world's rottenest keyboard here, so I appreciate you being patient with me. Okay, correlational approach is a research technique, and that's where you just look at whether two variables are related or more than two variables are related without manipulating the variables. What we're going to be talking about in these lectures is we're going to talk about the correlation coefficient. Correlation coefficient. And the correlation coefficient is sometimes used when you're using the correlational approach, but sometimes it's not. So you can use the correlational approach as a research technique without using the correlation statistic when you're all done with it. So let me describe an instance where you're using the correlational approach, but you probably would not use the correlation statistic to analyze the data. So let's say we're interested in whether actors or janitors are more depressed. So I randomly select, say, 30 actors. I randomly select 30 janitors. I have them all take depression tests. And then I want to compare the mean scores for the actors on the depression test and the mean scores for the janitors on the depression test. Now, what type of research technique is that? Well, I didn't manipulate people's occupation, right? And I didn't manipulate their depression test score. I didn't manipulate either of those, so I didn't manipulate the variables. But I am looking for a relationship between them. And if I'm comparing the mean score of the actors to the mean score of the janitors on the depression test, well, then the type of statistical analysis I would use would be, I'll wait for you to think about this, it would be the between subjects t-test, right? Because when you're comparing the means of two groups and you have different subjects in each group, that's going to be the between subjects t-test. So that research technique is the correlational approach. But the appropriate analysis for the data when you're done would be the between subjects t-test, even if you're using correlation, the correlational approach as your research technique. Now, for some times when you use the correlational approach, you'd want to calculate the correlation coefficient. And there are a number of different correlation coefficients. The one I'm going to talk about and the one we're going to compute is called the Pearson product moment. The Pearson product moment, which is a particular type of correlation. And what this is a statistic used to measure the direction and strength of the linear relationship between two variables measured on an interval or ratio scale. Correlation coefficient, Pearson product moment, a statistic used to measure the direction and strength of a linear relationship between two variables measured on an interval or ratio scale. So let's say you were doing the following research. Let's say you're interested in whether somebody's ACT score is related to their GPA. And so what you do is, let's say we randomly select 800 people who've taken the ACT. We get their ACT score, and we get their college GPA. Then we would calculate the correlation coefficient, the Pearson product moment, to see if there is a relationship between those two variables. So notice those two variables are both measured on an interval or ratio scale. I think they're both on an interval scale, actually. And so that's why you'd use this statistic, right? There is a correlation coefficient out there. It's called Spearman's rho. That is used for correlating variables that are on a ordinal scale. And you can even do correlations with things on a nominal scale, like the point biserial correlation and the phi coefficient are for data that's on a nominal scale. So you can do other correlations as well, but by far the most likely correlation that you would use is the Pearson product moment. Okay. Now, let's talk a little bit about this statistic, the correlation coefficient. The correlation coefficient, and for weird historical reasons, the abbreviation of the correlation coefficient is lowercase r, varies from +1, meaning a perfect positive relationship, to -1, -1, meaning a perfect negative relationship. And I'll talk about in a second what I mean by positive and negative relationships. Point of this is that the highest a correlation could ever be is +1, and the lowest a correlation coefficient could ever be is -1. And so let's say you're doing Stats Quiz 3 and you get R equal to 16,423. Well, bells and whistles need to go off in your head. If that happens, that's I made some kind of math mistake, because it's impossible for R to be greater than 1 or to be less than -1. So this is a way of expressing the relationship, or how strong the relationship is between variables. Now, the reason why r, lowercase r, is used as the abbreviation for the correlation coefficient, the reason is because the population parameter we're trying to estimate, so the overall, we're going to take a sample of data and get r, the correlation coefficient for that. What we're trying to estimate is the population value for the statistic rho. That's the population correlation, is rho, R-H-O, which is the Greek letter for r. That's why the Latin lowercase r is used for the sample correlation coefficient, so that's why it's r. Okay, well, let me explain what I mean by these things and try and show you what I mean by a positive relationship and a negative relationship. So let's talk about first a positive relationship, and this is a relationship in which as one variable increases, the other variable also tends to increase. That is a positive relationship. Relationship in which as one variable increases, the other variable also tends to increase. The way I like to think of it is it's when both variables tend to move in the same direction. And so saying it's a relationship where as one variable increases, the other variable also tends to increase, that is logically equivalent to saying as one variable decreases, the other variable tends to decrease. So in all cases, as one variable goes up, the other tends to go up, and as one variable goes down, the other tends to go down. Well, let me show you some examples of some variables that have a positive relationship. Let's say we did the following. Let's say that I had my computer set up to sound an alarm 10 times randomly during the day. And whenever the computer sounds the alarm, I've got a thermometer that shows both Fahrenheit and Celsius temperature on it. Whenever I hear that alarm, all 10 times, I'm going to go outside and I'm going to record the Fahrenheit temperature outside and the Celsius temperature outside. So I'm going to do that 10 separate times. And let's say I plotted a graph of the data. I have a bunch of graphs I made. I don't want that. Please don't do that. Okay, I don't want that. I want to make it bigger, though, so let me make it bigger. Okay, so here's what the graph of that data would look like. It would look like a straight line going from the lower left part of the graph to the upper right part of the graph. And the reason it would be on a perfect straight line is there's a perfect linear relationship between the Celsius temperature and the Fahrenheit temperature. You probably learned this in elementary school. There's an equation you can use to convert from one to the other. So if you know the Celsius temperature outside, you can perfectly predict what the Fahrenheit temperature is outside. And so if you got a relationship like this, where all the data points lie along a line, the straight line that's going from the lower left to the upper right, that's as perfect as a relationship could be. If we calculated r, the correlation coefficient for this data, r would be positive 1.0, meaning it's a perfect positive relationship. The sign on the correlation tells you the direction of the relationship, in this case that it's positive, so as one variable increases, the other increases. And what you should look for in a graph for a positive relationship is that most of the points should be in the lower left and the upper right part of the graph. These two quadrants here should have most of the points, with fewer points than these two here. That shows you got a positive relationship. Now the one shows that it's a perfect relationship, and what that means is knowing the Celsius temperature, we can predict the Fahrenheit temperature. However, most of the relationships we study in psychology are not perfect relationships. Let's show another. Here's a very strong positive relationship here. This is a scatter plot of height and weight for a bunch of people. I think maybe 200 people. They got the height and weight for those 200 people. And that's what's shown here in the graph. And what you can see is now, I mean, most of the points are in the lower left and the upper right on this graph, right? But it's not like a perfect line between them. And knowing somebody's height, we can't perfectly predict their weight, right? That's why there's not a perfect relationship between height and weight. And that's because it's quite possible for two people to be the same height but different weights. But there is some relationship, and the relationship is a positive one. As height goes up, weight also tends to go up. If you calculate the correlation between height and weight, R is about positive 0.8. It's positive because, as you can see, most of the data points are in the lower left and the upper right. It's really a strong relationship because the points are lying, very, very closely along here, close to a straight line, and very few in the upper left and the lower right. So 0.8 is a really, really strong positive correlation, but it's not a perfect correlation. So there is a positive relationship, and a very strong one, between these two variables, but it's not a perfect positive relationship. All right, let's show you a weaker positive relationship. What I did is I took everybody's Stats Quiz 1 scores and their midterm 1 scores, and I think it may have cut off a few out here on my graph. Sorry, let me move that up a little better so it's easier to see. Hard to make this bigger. So that's as big as I'm able to make it. Okay. Well, what this is somebody's midterm 1 score and their Stats Quiz 1 score. I don't know if you can see, but most of the points are like here and here. They're in the lower left and the upper right of the graph. Very few over here. And so what that means is there is a positive relationship between these. As somebody's midterm 1 score tends to go up, their Stats Quiz 1 score tends to go up as well. But it's certainly not a perfect relationship. And this is sort of I would call a moderately strong relationship. Correlation here is positive 0.5. And that is, there is a strong, a positive relationship, moderate relationship. But you can see that from knowing somebody's midterm 1 score, I'm not going to be really very good at predicting their Stats Quiz 1 score because the correlation isn't super, super high. All right, last one I wanted to show you of a relationship, positive relationship in a real graph was I took all the 50 states, and for each state I looked at, this is from the last census, 2010, looked at the number of people who live in the state, and then I also looked at the area, the square miles that the state covers. So the size, physical size of the state, as well as the population size. And I wanted to see if there was some sort of correlation between those two. And I wasn't sure how that correlation would go when I first started doing the graph, because there are a lot of states like New York and New Jersey on the East Coast that aren't really very big. They're small states, but they have a lot of people in them. And then there's states like Wyoming and Montana that are really big states in terms of land area, but have very few people in them. But then there's states like California is the most populous state, and it has the most people. And so I wasn't sure if there would be a positive relationship or not between the state population and state area. So let me show you what that graph looks like. It looks like this, and blow it up a little bit. Okay, so why is it? I don't know why it's doing that. All right, so you can see the correlation here is positive 0.08, and maybe it's hard to see the dots. But what you got is here's area down here, population here, and so almost all the dots are clustered down here. One of these is Iowa. I'm not sure which one. But then we got a few extreme scores out here. I don't know if you can see these or not. You know what this state is out here? I'll give you a second to think about it. Yeah, that's Alaska. Really huge state with almost nobody in it. So Alaska's way out here. You might know this state. This is the most populous state, and it's pretty big too. One of the biggest states. All right, that's California, so it's the most populous. And then here's another state. It's a little less populous than California. Still one of the most populous states, and one of the biggest states too. And yeah, that's Texas there. This is Texas. Okay. But the point of this is there's almost no relationship between these two variables. This correlation is positive, but it's not statistically different from 0 for this set of data. And we're going to talk about later, probably on Wednesday, about the effects some of these extreme points are having on the data, because extreme points like that can have a big effect on the correlation. All right, so that's the idea of what a positive relationship is, and there we go. Positive relationship is a relationship in which, as one variable increases, the other variable also tends to increase. Another way of putting it is the variables move in the same direction. All right, let's talk about a negative relationship then. And that is a relationship in which as one variable, all right, as one variable increases, the other variable also tends to, no, the other variable tends to decrease. All right, relationship in which as one variable increases, the other variable tends to decrease. That's a negative relationship. And what we mean by that is that the two variables move opposite of one another. As one variable goes up, the other one tends to go down. Now, here's an example of a perfect negative relationship. I couldn't come up with any real-world variables that had a perfect negative relationship, so I drew one. So here's our x variable and our y variable. And what I tried to do is draw all the lines, the dots on a nice straight line that goes now from the upper left to the lower right. It goes this direction. And that's going to be the key for identifying a negative relationship. If most of the points in the graph are in the upper left and the lower right, that's going to be a negative relationship. Now, since these lie on a perfect straight line, that's why a correlation here, r is negative 1.0. What that tells us is there's a negative relationship. As x goes up, y tends to go down. The negative sign tells us a negative relationship. And the 1.0 says it's a perfect negative relationship because the points lie in a straight line. If I know the value of the x variable, I can perfectly predict the value of the y variable. Now, some variables in the real world are negatively correlated. Here would be an example of a variable that's negatively correlated. So if we measured how much alcohol somebody consumed and we had some sort of test of their motor skills ability, those would be negatively correlated. That is, the more alcohol you drink, the worse your motor skills are going to be. It's not going to be a super strong relationship because, of course, there's lots and lots of variables other than the amount of alcohol you've consumed that determine how good your motor skills are. But the data here would be about a correlation of negative 0.4. Negative 0.4 would be the correlation here. So I would say that's a moderate negative correlation, a moderate negative correlation. And you can see most of the points are in the upper left and the lower right. That's what tells you got a negative correlation. All right, well, so you understand positive and negative relationships. Let me show you this graph and see what you think of this. So here's two variables, x and y. And if I were to calculate r, the correlation between these variables, what do you think I would get? I'll leave you a chance to think about that. Well, what I get is r very, very near to 0, r near of 0. And the reason why is there's really no relationship between x and y in this graph. As x goes up, y is just as likely to go up as it is to go down. And so what that tells me is there's really not a relationship between x and y. There's no tendency for y to go either up or down as x goes up. And that's when you got an r equal to 0. No relationship between the variables. All right, let me show you another one, see what you think the correlation is with this one. All right, here's the x and y, and now the points lie on a perfect straight line like this. I tried to make it a perfect straight line. So what's the correlation between x and y in this graph? Okay, well, the correlation is 0 here as well. If we computed r, it would be 0, even though the points lie in a straight line, because there's no tendency for y to go up or down as x goes up. That is, no matter what x is, y is always the same thing. That's why there's no relationship between x and y. So r is 0. So what I hope you've gotten from the examples I've given here is a really, really strong positive relationship. That's going to have a correlation near 1. A really, really strong negative relationship. That's going to have a correlation of negative 1. And so a correlation where there's no relationship between them, where y is just as likely to go up as down as x goes up, that's going to be a correlation of 0. So the closer you get to the 0 correlation between two variables, that means there's no relationship. The stronger the relationship is, the higher it gets to positive 1 if it's a positive relationship, and negative 1 if it's a negative relationship. Now, what I would say is we're very, very rarely dealing with extremely strong relationships in psychology. I would call a strong relationship a correlation of, I would say maybe 0.6 or above is a really strong relationship. So higher than positive 0.6 or lower than negative 0.6 are very strong relationships. I consider correlation of 0.4 or 0.5 or negative 0.4 or negative 0.5 moderate relationships. And then correlations below 0.4 are kind of weak relationships, I would say. And in psychology, we're very, very often dealing with correlations around 0.2 or 0.3. Okay, so usually not very strong relationships. So that would be very common to deal with correlations about positive 0.3 or negative 0.3 or so. Okie doke. So that's my introduction to what correlation means. And so what I'm going to put down is now watch the video about how to do the correlation. Now, when the TA made the video, he was using the textbook that we had last semester, and so he refers to some page numbers in the textbook. Just ignore those as you're working the problem. But the instructions for doing the correlation, you should look at those. They're on the Canvas site on the front page. And then you're also going to need the T and the F table, T table in this case, and that's on the front page as well. So that's the end of my part of the lecture. Now you need to go watch the TA's video. Okay? So I'll have a new video up on Wednesday.